Hello, it's Adrian from the Data Science class, and I am going to take you through my presentation. My presentation is about binary classification of the author of a tweet sent out during the 2016 election, Donald Trump versus Hillary Clinton. Who wrote it? We start with this reviewed Kaggle dataset. I don't think they've ever done like a competition based on it, but it is up here. You can get it if you have a membership, and the membership is free. It's an interesting set that includes who wrote it, how many times it was favorited, retweeted, that kind of thing. The problem for me is that it was only 10 features wide. So I wrote this Python function that finds, using some conditionals and list comprehensions, a bunch of metadata, and I'll show you exactly what they are later. Then I implemented it in this quick and dirty little script to put 14 more columns into that CSV. We're going to run this in the background so we can prove that everything works, and then we'll take a look at the PDF because it's a little easier to read when we're working through this. So here we go. In terms of the framework, my business goal is to understand who wrote this and be able to produce a classifier that can tell with, let's say, 80% accuracy, or whatever, who wrote it. And I want to be able to do this with only numbers because it is difficult to derive context, word stems, English syntax, any other language syntax. So I figured if I used numeric metadata, it would be putting the ball in the computer's home court, and if you could have more of a lightweight option for classifying text, that might be helpful. That's my thesis, if you will, for this project. So here's the original data set. You can see we have some retweets, authors, in reply to screen names, language, retweets. And then I left the capital letters on mine, so the ones that I'm engineering are over here, and that's why you can see that they're all numeric. I got rid of the number of columns because it was messing with the CSV function, but we don't need it. Then I used dummy encoding to get a bunch of ones and zeros for the booleans, Clinton, Trump. And the numeric factor ID number type categorization for the languages and who they're retweeting at, so everybody gets their own number, each language gets its own number, etc. I just iterated through and turned them all to numerics. Here you can see what it's looking at now. Now, quick note on NAs and imputation, outliers, that sort of thing. I used the complete cases function, and that only lost me 7 records, so I don't have a lot of NAs because I engineered most of this data myself. As for outliers, I opted not to remove them because I'm predicting a binary. If I was predicting a continuous variable, I probably would have. Not that it couldn't still mess you up, but I wasn't sure what the significant values were going to be just yet, so I thought I would find out what they were, take a stab at modeling, see how it went, but I will show at the end how I would have imputed and found outliers and things like that, just to demonstrate that I know how to do it for the purpose of academia. After checking that we have a pretty fair distribution of Hillary versus Trump tweets, here we are. If I was to do some imputation for missing values like the booleans, like was it a truncated text, was it in reply to somebody, you can see based on the proportions it would be very easy, very safe to just give the negative. Most of them weren't truncated, most of them weren't in reply to somebody. Easy imputation there. For the continuous variables, I have information on mean and things like that. I could impute if I wanted to, but I don't have missing ones to such an extent because I engineered this. The first look was just to get an idea. I have no idea if any of the things that I've created mean anything to anybody, let alone a machine. So I wanted to see if any of them were statistically significant, just to see if there was anything for the machine to sort of grab onto when it was analyzing. So I looked at some things like average sentence length and did a quick Pearson check. Pretty soft correlation here, even though it seems different. Almost no correlation for average word length. Retweets, they do seem to have different retweeting habits. Sharing quotes, I did this for a bunch of them. I'm not going to go into all the detail for time's sake. Some of them were basically meaningless. Use of all caps, things start to get a little more interesting. We do have a Trump skew here. I have her as 1 and him as 0. Note that as because Clinton comes before Trump, I'm not trying to say anything by making her as 1 and him as 0. So I opted to quantify those and visualize them. For favorite counts, we see a pretty heavy Trump skew. So as that's the new high water mark, I diagrammed that out. The partitioning of the data set was quite vanilla. Training index with the caret features. We use caret heavily with this. I did throw away 1 to make it so there's an even number in each. One model didn't, like when I had like 3000 and 3001. First model we tried was a basic linear regression model, which I rounded to get a binary outcome. And the root mean squared error is very similar to the percent accuracy, and that's not a good sign. So we're not going to use that model for the ensemble, but it was worth it to get some insight into what some of our statistically significant data is. And honestly, I was surprised to see a lot of these, at least according to this model, are significant, including almost all of the engineered ones. So Yahtzee, we're going to try to build a model. This suggests that it's worth giving it a shot. I just get rid of the old prediction, and we're going to try KNN. Want to factor our stuff, and we're going to use the caret function so we can smooth the tuning process a bit. Now, we see an accuracy in the 70s. 0.46 root mean squared error is not great when you're doing a binary. I mean, the bar to beat is 0.5, so we tuned it, and we get to a 0.82, 0.42. I'm going to give a similar analysis to the rest of the models just so I don't have to, keep saying the same thing over and over again and drive you all nuts. So we're going to do simple accuracy, root mean squared error, and if they show some promise, we're going to do an area under the curve by visual and by metric. And so that's looking like something we might be able to get something done with. Now the neural net comes next, and because even when I use the invisible function in R, it produces pages of numbers, I didn't include it in this PDF, but it was a simple training, just like the other one, and we're going to give it the same treatment, where you have a better starting value for both of these features. And with some tuning, we can improve them both a little bit again. So we're going to keep that. Should be familiar. And we get our metrics for area under the curve. Rule learners. In terms of how I selected these models, I basically just tried all of them and threw the ones that didn't work away, and I used ones that were good for numeric data. There was nothing more complicated than that. This one I picked because it produces a human readable output. We'll get to that in a sec. I just used the JRIP function from R-Weka. I didn't use caret because it's very easy to get the output for this one, and that was why I did it. Honestly, these stats are okay. And here is some interesting human usable information. For example, exclamation points are a signature Trump move in the majority of cases versus Hillary Clinton. Having a lot of favorites and no periods is a sign of Trumpdom, apparently. That sort of thing. Just because neural net's a total black box, and KNN isn't much more accessible to human either. So I want to try a random forest also. We've had some good results with those, and here's where things get interesting. We have 100% accuracy and no error. Now, honestly, this was more of a red flag than an excuse to start popping champagne, really. These do tend to overfit. So because I only have 6,000 cases, I didn't want to do a full holdout method. So I opted to use 50-50 for training and validation, and then bootstrap something for this to reevaluate this. I made another training index and drew another random half and ran the analysis again, and we still ended up with a pretty good number. I tried running it in the whole data set, another sampling, another 50, and another 50, and still performs pretty well. So I'm going to keep it in the ensemble, with the caveat that in using it alone, I'd be very wary that it would overfit. But it's going to be an ensemble, which should help with that. In terms of creating the actual ensemble, I created a column for each of the models that we've done that I liked, which is basically everybody but the regression model, and gave them a column to make their prediction in. To break ties, and because it was the highest performer, I gave the random forest 2. Now we have 5. And then I just made a vote function, just iterated through, and at each of those columns I tallied it up, and we have our vote. So when I performed this ensemble prediction, we end up with a 96% accuracy, and here's our error, which is pretty low. So it does seem to confirm the thesis that you theoretically can tell who's talking, which only based on the numbers of their words, not the choice of their words, which is interesting. At least in this case, obviously this is sort of proof of concept, very, very lightweight, not heavy duty sort of thing. And our numbers look pretty good here too. In terms of deployment, could get a little bit high maintenance because you have a couple different libraries. It depends on the language that you're using and all that. Now, just to be diligent here, I made a support vector machine where I would demonstrate some of the outlier detection and things like that, and I'll run that. We can see here that my code all ran just fine, but we do want to show some running code. And when we create this model, we can then use the z-scale normalization on everything but the handle, which is why it's I in 2 through, not 1 through. And then you use that index to easily subtract 3, 1.5, 4.5. Depends on your data set. There's a considerable amount of judgment and wiggle room here. You could argue all day about whether or not to leave them in, take them out. And this shows that it subtracted something, and we see we can make a prediction, and it's not that good. But I just wanted to show that it was working. It just asked to show some more running code, so I just wanted to demonstrate up here that this works. And this part is relatively quick. The model's already created here, and we can train these pretty quickly. So there's our evaluation for numbers and a quick demonstration of how the models run. Here's some quick computation to see how everything worked out. I just want to say thanks for a great semester, and I will see you in the comments. Have a good holiday.